Behind me is a cathode, and behind you would be the anode mixers. They are more or less the identical. They have identical machines. It's just that the cathodes here, the anodes here, we like to keep the materials separate. So we can go down slowly down in this direction. The mixers we have are a prototype scale, so they are something like 50, 60 liters or so. We have a couple of these on both sides so that we can go through a few different mixing batches. The primary objective of the prototype line being to test different materials for processability, performance, and various other things that we like to test. So we can go a little bit further in this direction, I guess. We've got a small display for visitors, but I think you'll be quite well aware what most of this is. So we've got a sample of different materials that we're using. So this is an example of a coating machine we've got in our prototype line. It's a regular coater. We haven't the coating process itself isn't a focus of our innovation. It's more to do with the chemistry. So we want our chemistry to be applicable through many different processing methods. So we've got a representative coating line here, and then it goes through the dryer with a typical coating process. Typical, I'm not sure if that's the right word, but it's the coating process we have. Yeah. It's not very visible, but we have a number of quality control points inside there, including position controls and load cells that measure the coating weight of the coating to make sure that we've got everything to specification, and they are both monitored on both lines. And we calendar the electrodes so that they reach a consistent and required target press density. We found that our anode material especially is more difficult to calendar. It requires some more parametric tuning to calendar our anode materials to required specifications. So the calendar unit does face a little bit more challenges. It basically has to work a little bit harder. We've overcome those challenges in the past couple of years, and now we're able to reach the required specifications that we've designed into our cells. So yes, that has been a challenge and also a learning process as well. It's not graphite is very soft compared to our material. Graphite does calendar quite easily. It kind of gives because it's also an industrial lubricant as well, right? But for our anode material, we found that it doesn't really want to give, so we have to kind of massage it in a way. Yeah. So this door leads to our material lift because we don't want to wheel all the material back out to the corridors. So all the material that's prepared here goes into that lift, and then it goes up to the second floor where we do subsequent processing like assembly and so on.
So here we can test new materials and make cells up to a pre-A sample.
Come in with me. Come in with me. Come on with. So after the air shower, so we are surrounded by various different machines. I think it'll be best to start from the back where the material comes up. Through the back here is where the material lift comes up from the first floor where we have prepared our electrodes. And then it comes up through this rolling door here after the air showers and everything. And then it comes up here to this area where we what the material looks like at this point is it is in rolls of, it's a small one, but it looks like this, obviously much bigger. It's in a roll of electrodes. It's either silvery for the cathode or copper based for the anode. And then we have to prepare them for assembly. So the machine behind Cecilia, who is not in the frame magically, is the die cutting machine. This machine will be responsible for the die cutting of the electrode rolls, and it's basically just a stamp that cuts out the electrodes to shape so that we can stack them directly. This is a prototype line, so we stamp them out directly in a mass production environment that you may have seen before. A combination of slitting and stamping procedures might be used, or laser cutting, or any combination. It goes in here, and the material flows in directly into this machine. This machine is our stacking machine. So basically the prepared anodes and the cathodes go in here, and then we've also got a stock of separators that goes up in there. So the separator, the cathode, and the anode all get stacked together quite literally in this machine, and then they become what is the core of the cell that we put into our batteries. This is a small version of our cell. So this is what comes out of the stacking machine, and then this is what we weld on. It's basically the current collector tab that interfaces the outside world with the stack inside. And yes, this is the welding machine here that you see. Again. Okay, so what we've got here, this guy, this machine is responsible for preparing the three-side sealing of the aluminum pouch. So the stacked cell goes in here and then it gets sealed around. And this is what we prepare with this machine. So this is the injection machine that we've got. Previously, we have prepared this with the stack and inside the pouch and everything. It is obviously not yet filled with electrolyte, which we need. It's kind of the blood of the cell. So this goes into the machine. It is connected to our electrolyte tank that you might see on the left of the frame, maybe very slightly. But yes, we've got a lot of plumbing in here that goes in and it injects the required amount of electrolyte inside here. You can see that right now we've taken the gloves off. You can see that this entire area is completely controlled. It's basically nitrogen purged, right? So we've got nitrogen purging inside there so that we ensure there's no moisture going inside the cell. And then all the injection chambers are all vacuum filled as well. So that was the entire assembly process. Okay, so this, what you see here in front of on both my sides is the formation machines. What we do here is we pre-charge the cell. This is it's quite a typical process, I'd say, in most battery processes. What we do here is we bring the cell up to voltage and we form the initial SEI on the cell on the anode typically. And these are what these two machines do. You'll see that one is enclosed and one is not. So we've been doing a series of experiments. One is obviously in a room environment where the temperature and so on is not controlled. The other one is in an enclosed area where we control the temperature. So this is typically for chemistries that require a high temperature formation process, something like 35 to 45 degrees Celsius that we want to do this at. So we've got basically two environments that we can play around with our formation protocols for our different material studies for our cells. This is set up to fit our prototype cell dimensions. We can also fit our full cell dimensions. They only differ in thickness, so the length and width are more or less the same. So we can fit them in. And these are all automated, so we don't do too much manual work here, apart from, I guess, loading is manual. We've been optimizing our formation protocols to take it down from something like 48 to 50 hours down to about 8 hours because we want to fit it in a working day. We're working on shortening that and also improving our throughput of the formation process as well. So this machine is our initial testing machine to test the open circuit voltage and also the internal resistance of our cell. So it's basically stick it in and we do a quick measurement. We do this for all of our cells. So this is a complete test to sort out if there are any issues. So far we've had very few issues. If the welding wasn't good or if there was a disconnection somewhere because of some flaw in some dramatic flaw, then we can quickly sort it out. But so far we've had no such issue. So it's more of a let's just make sure kind of thing because it's a quick test. So where we are today right now is the materials lab. This the main activity we do here is to do an initial screen of the different materials that we'd like to test and experiment on. Different types of cathode and anode materials, different types of separators and so on. So it's the solid powders that we more or less concentrate on. We've also done some small studies, maybe not so small, studies on the different substrates we use, the aluminum and the copper foils. So this is where most of that material level study happens. We do small scale slurry mixing. We have a Carl Fisher here, which actually should be moved back. Behind, we also have the small calendars. So this basically the objective of this lab is to do number one, material studies, number two, lab scale feasibility studies of the material in a battery context. So we also aim to prepare coin cell materials here as well. And yeah, so all the machines that you'll see here are more or less catered and laid out to that end. So we are here at the coin cell testing area. Previously, we were at the materials lab where I mentioned that we are preparing the materials for coin cell preparation, but the actual coin cells are prepared behind you where the glove boxes are. So I can go over to the glove boxes. So the main assembly of the coin cell itself is done here. So basically it's a rather manual process. It's also a bit of an art to it. But behind me in the larger glove box, we also do a lot of electrolyte studies as well. So some of our colleagues are mixing a lot of different kinds of magic formulations or potions or whatever for the electrolytes that eventually go into the coin cells for electrolyte studies as well, to find out the best electrolyte composition that works with our cathode and anode active material combinations. So yes, so after the coin cells are prepared, then the coin cells will be tested at our various cyclers here. So where we are right now is the testing area of our cells, where we put through our where we put our cells through its paces. This machine that you see here, we use for our very high rate testing. So this machine puts out something like a combined 3,000 amps or so to really put our cells through its paces. This machine is connected to our temperature control or environment control chambers here, where we also can bring the cell down to minus 20, 25 degrees Celsius or up to some arbitrary temperature to also see how the cell responds at various extreme conditions. Today we use this for also high power testing. Obviously with a high current you can control the power as well. But we've also been testing our cells over very, very long durations as well. And I think we've recently passed a milestone of 20,000 cycles with our current cell design that we have already commercialized. This is 20,000 cycles at 5C, up and down 5C, 5C. And we have shown that it retains well above 70% stellar health. So this is an important milestone as well, because previously we had designed and really kind of aimed for a milestone of 10,000 cycles, which we easily passed. And now our cells are showing pretty good performance at even 20,000 cycles. So this is not a projection or a simulation or a calculation. This is 5C up and down for the past year and 2 months or so. So we've really been continuously testing non-stop, and to show that the results are basically the real data. And I think we'll be able to release some results as well. Thank you.